Welcome back everyone to this video series about networking. My name is Bruce Hartpence, a faculty member here at RIT, and I will be your host. Thanks very much for listening. This week we are covering Chapter 5 in the Packet Guide to Voice over IP from O'Reilly, and so we're going to talk a little bit about codecs. So without further ado, here we go. A codec, or coder-decoder, has a very particular job. It has the purpose of converting analog signals into digital data for transmission, and then at the receiving end, it converts it back again. And the best example that we have is human speech, right? So we do this all the time, and the codec converts the analog voice signal into those ones and zeros. Now, at the other end of the transmission, you have to take the ones and zeros and turn them back into something that looks a lot like the original analog signal. So when you're calling grandma, you have to be able to convert and then decode again, or code and then decode. Now, when we think about a codec, it is software and hardware that works toward this encoding of the audio or the video signal. And the codec can be located in the phone, it can be located in the PBX, or the switch itself. Generally speaking, when we talk about codecs, there are two flavors. We've got audio codecs and we've got video codecs. The audio codecs are covered by the ITUT G series, or at least the most popular ones. And so I've listed some of those here. There are lots and lots of techniques for encoding audio. We're going to talk about one called the waveform technique in G.711, but more on that a little bit later. There have been a couple of efforts in the encoding of video, and these are covered by the ITUT H series and by the MPEG standard, with the H series going in H.261, H.263, and H.264. And we've seen MPEGs, MPEG-3s, MPEG-4s. MPEG-4 and H.264 are where the two standards efforts sort of came together a little bit. Whether you're doing audio or video, we start off with a process called pulse code modulation, and then we modify it a little bit. So it doesn't really matter what type of technique you're applying to encoding the audio. You're going to start off with something that looks a lot like pulse code modulation. And so that's the one that we always talk about to explain how we encode and then decode audio signals. And this is standardized in ITUT G.711. There are a couple of parts to the process. First, we have the sample of the voice signal, and then we have to quantize it or apply values to these signals based on their amplitude. Now, a voice channel or telco system is based on the frequencies that can be generated by a human. So I talk a little bit about these in the chapter in the book. So when we talk about human communication, there are two sets of frequencies that we think about. One set is the frequency that we can hear. And so we can hear up to about 20,000 hertz, maybe a little higher, maybe a little lower, depending on your hearing loss or how good a hearing you have. And then there are all the sounds that you can generate. And the sounds that you can generate are a subset of those that you can hear. So the frequencies that we can generate are about 0 to 4,000 hertz. The channels for communication don't have to be based on what we can hear, they're based on what we can say. You take this voice signal that you're speaking, and you have to now sample it. So now the question is, how do we take samples? Well, sampling just means that you're going to measure what the signal value is so many times a second. Now, if you do it too slow, that is, you don't have enough samples, then you can't accurately recreate the signal. And we actually get something called aliasing. If we do it too much, then you've got a lot of extra data that you're never going to be able to use anyway. The right amount of sampling comes from Nyquist and Claude Shannon, and it turns out that the right value is twice the bandwidth of the incoming signal. So if the channel is 4,000 hertz, we sample about 8,000 times per second. Now here is a sample audio snippet. Turns out that this is just me saying the word hello 3 times in a row. But if I take a portion of one of these words and expand it, that's what the actual audio signal looks like there on the bottom. So now what we have to do is so many times a second, we have to figure out what each one of those values is going to be. So if you can imagine a bunch of samples, all trying to measure what the analog signal is doing at that particular point in time. So here is a grid that I'm going to overlay on top of this audio signal. And the red arrows indicate some of the sample values. So all the vertical lines are where I'm going to take sample values. And these red arrows happen to point out problem areas. So the vertical lines are where we're going to take our samples, and we do this a whole bunch of times a second. The horizontal lines are the actual values that we assign to the samples. So here's the problem. If we have a certain number of horizontal lines and the values don't fall right on one of those horizontal lines, we have to figure out which one of the horizontal lines we want to use to represent the sample. So any value that doesn't fall right on the line, like those indicated by the red arrows here, are going to result in what we call quantizing errors. So we have a couple of problems when we're trying to figure out what we're going to do with this analog signal. How often do we sample it? And then for each sample, how many bits per sample, or how are we going to accurately represent the magnitude of the sample? It turns out that with human speech, we want to use about 8 bits per sample. This gives us about 256 possible values that we could assign to our individual sample. So 8 bits per sample, 8,000 samples per second, that's where our 64,000 bits per second data rate comes from. So now that we have a basis for understanding how we do our encoding of the audio, we now have to sort of sit back and think about how this really works. All right, so you're sitting there, you're talking on the phone, and your analog signal, your analog voice, is sampled and then quantized, and then the digital data is sent toward the other end. And at the other end, the digital data is reconfigured to recreate the analog signal. Now I mentioned that there are a lot of different codecs that we could use for this, and G.711 represents this thing called pulse code modulation. But pulse code modulation takes that 64,000. Most other codecs take less data rate than that, or a lower data rate. So which one do you use? So when you're making a codec selection, you have a couple of questions that you have to ask yourself. What are my performance expectations? It turns out that it's very tough to beat G.711 in terms of clarity and performance. But, as I mentioned, it does take 64,000 bits per second of bandwidth. So if you're somewhat limited, and sometimes WAN connections are, sometimes we pick a codec that takes less bandwidth, G.729 for example. Now one of the other things that you have to consider are the collection of codecs that might be in the system. So what is the source codec and what is the terminating codec? Some codecs work better with others. So if I encode with G.711 and you try to decode with G.729, what does that mean? Sometimes there are losses between codecs, and we call those transcoding errors. Another problem for some codecs is packet loss. Packet loss makes it very, very tough to recreate the analog signal at the other end. So packet loss concealment is a technique that a codec uses to sort of determine or guess what the data was going to be if the packet hadn't been lost. But packet loss concealment actually takes a certain amount of time to accomplish, and so you're trying to fix a packet loss problem, but you're creating latency in the codec. So it's sort of a trade-off. You have to decide what you want to do. Most codecs also include some form of compression, and so we have to ask ourselves, how much compression do we actually need? The last thing we'll talk about today is video. Usually in video we're sending a series of pictures, and when we're sending a series of pictures, particularly when we start talking about lots and lots of resolution and lots of color depth, then we start to get into big bandwidth. Video is also analog data, and so we start with approaches similar to PCM, but then we have variations on a theme. So with video streams, what we're trying to figure out is how can we compress the video, how to recognize repeated information and take advantage of those patterns, and then do we send all of the picture, do we send the moving parts? So these are all decisions that we make as we try to transmit video. And then of course there is how much color do we want to provide and things of that sort. Well, I think that'll about do it for this week. This has been Chapter 5 in the Packet Guide to Voice over IP. Next time we'll talk about RTP and RTCP, which is the set of protocols that Voice over IP systems use to packetize the audio and video samples that we've been talking about today. You can cruise around brucehartbents.com, see what kind of stuff we've got out there, and of course there's the videos in the various channels here. Thanks very much for listening, thanks very much for watching, and may your packets always reach their destinations.